Hello, everyone. Welcome to your first physiology lecture for the year. So in the respiratory system, the very first topic we're going to be covering is the biomechanics of breathing. So let's get started. So these slides will be covering this topic. And in doing so, we'll touch on a couple of key areas. The first one being pulmonary or mechanical ventilation, which is just a fancy way of describing breathing in and breathing out. And also the factors that influence it. So we're going to talk about lung compliance, how easily the lungs expand, and in doing so, discuss things like elastic recoil and surface tension, as well as discuss the role that airway radius plays in influencing our breathing. And then finally, we're going to be talking about one way that you can investigate lung function, and that's through spirometry. We won't be spending too long on it though, because you have a dedicated video just for that. We're just going to be briefly touching on it and leaving the rest for our wonderful team to discuss in a different video. Now, one thing that I want to make absolutely clear is that although we're going to be throwing around a lot of jargon and a lot of medical terminology, it's important that you remember the big picture, is that this whole topic is just about breathing. So when I use the word ventilation or mechanical ventilation or pulmonary ventilation or the thousands of other different ways you can probably refer to it by, just know that I'm talking about breathing. So inhalation and exhalation. So that's another very important principle, just to keep in mind, big picture idea. This is all about breathing. All right, so now that we've got that out of the way, the very first thing we're going to be talking about when it comes to breathing is the two main stages and how they work. So that's inhalation and exhalation. So when it comes to inhalation, this process is very active. And so what happens is your respiratory muscles during inhalation are actually contracting. Now, you would have learned last year a little bit about the respiratory muscles, but we'll just revise it very briefly. Your principal respiratory muscles is mainly your diaphragm, but you also have other muscles involved, like your external intercostals, and in a more extreme scenario, sternocleidomastoid and your scalenes. However, the one that we really care about the most, which is the biggest, primary muscle for respiration, is your diaphragm. And that's sort of shown on this slide with that red band of muscle there. Now notice that during inhalation, the diaphragm contracts and goes from being an arch shape to a taut or rigid flattened shape. So you can imagine it as the diaphragm going from an arch like that, and then once it contracts, it pulls its fibers out, and so it pulls its fibers in and becomes a very tight, flattened structure. And so you can imagine that because the lungs sit on top of the diaphragm and the diaphragm is moving down, it actually is pulling the lungs down with it and also expanding the thoracic space. So very important idea, understand how the diaphragm works, and then understand that because of the way the diaphragm works, because of the fact that it's contracting and flattening, it actually increases the space inside the thoracic cavity. So respiratory muscles contract, thoracic space expands. The next important idea is that your pressure inside the thoracic space is then going to drop. And that makes sense because if you imagine the volume of inside that container, the thoracic container, has increased. So you can think about it as being more space for gas to occupy. So it can wiggle around without much trouble. And so there's less pressure there. So again, thoracic cavity pressure drops, but more importantly, it drops below atmospheric or outside pressure. And that's important because one thing you would have been emphasized over and over again in physiology last year is that things like moving down gradients. So like going from areas of high concentration or high pressure to areas of lower concentration or lower pressure. So in this case, what's going to be happening is because the thoracic cavity pressure has dropped below the atmospheric pressure, the air from the outside, which is at a higher pressure, will want to come into your lungs where there's a lower pressure. So it'll do so. So your air is going to rush in as a result. So you can see your respiratory muscles contracting directly leads to air rushing into your lungs. So just have a look at these steps and see if you can figure out how they work and why they work. And then once you do that, we can move on to exhalation as well. If it's still a bit tricky, I think a useful analogy to use is that of a syringe, right? So you know that when you pull back a syringe, it sucks up fluid. It's very much the same principle. What's happening here is the diaphragm is sort of acting like the plunger. It's increasing the space inside the syringe or inside your thorax. And instead of sucking up fluid, it's allowing us to take in air into our lungs. So you can use the analogy of an unsealed syringe, unsealed being the fact that the tip is open to the outside air. That'll become important later on, but that's an analogy that you can use to describe inhalation and exhalation. The next step, though, once you've inhaled, is to get rid of the air that you've inhaled, and that's exhalation, right? We are skipping something in between, which is what's going to actually happen to the air that you inhale. And again, that'll be covered in a different topic, which will be done by our team, which is called perfusion. But we'll move past that onto exhalation. We've assumed that we've dealt with the air, we've done whatever we want with it, and we now want to get rid of it. So that's exhalation. And pretty much the opposite occurs here. So where your respiratory muscle was contracted and flattened in inhalation, it's now going to become relaxed. So it's going to go from that flat shape back to that arched dome-ish structure. And when it does that, you can imagine that where your thoracic space was enlarged before and bigger, it's now going to shrink and it's going to become smaller. And you can think of that as either physically pushing the air out, or if you're describing it in terms of pressures, you've decreased the space inside your thorax, and so there's less space for gas to wiggle around in. So there's an increase in the pressure. It's sort of pushing things around and knocking into the gas particles next to it more frequently and more intensely. And so there's an increase in the pressure in the thoracic cavity. And probably most important idea again over here is that the thoracic cavity pressure actually rises, but it rises above atmospheric pressure. And why is that important? Well, again, things are going to want to move from a high pressure gradient to a lower pressure gradient. And so in this case, because the pressure inside of our thorax has increased above the outside, the air will want to leave our thorax and leave our lungs and rush out. So exhalation moves air out. So you can see in both inhalation and exhalation, it's the direct role that the diaphragm and your respiratory muscles are playing that results in air either rushing in during inhalation or leaving via exhalation. And again, the syringe example still holds true because what's happening here is the diaphragm is acting as a plunger. This time it's actually pushing forward and reducing the space in that syringe and pushing, in this case, not fluid, but air out. So again, a very useful analogy to use. Now, it's all well and good to be able to understand the principles behind inhalation and exhalation, but it's also very important to be able to graph these changes that's occurring inside your lungs. So within your lungs, intrapulmonary, the pressure changes. We can look at what's happened to them over time as you breathe in and out and map that. So for example, during inhalation or inspiration is another way of describing it. We know our thorax is expanding, and in doing so, our thorax is expanding because, again, our diaphragm is contracting to flatten, increasing the space in our lungs. So in doing so, the intrapulmonary pressure actually drops because you've got a larger volume for gas to occupy. So that's why if you look at the graph here on the right, you can see that during inspiration, there is a drop in pressure, and that's relative to the outside. So it's going to be a lower pressure relative to the outside. But then there's a weird thing that occurs where it becomes zero. And the reason it becomes zero or equalizes with the outside pressure is because, sure, your diaphragm contracts and the thorax expands and the pressure drops. But that pressure drop is going to make air want to come in to equalize that pressure, to move from a high pressure gradient outside to a lower pressure gradient on the inside. So it does that, and it keeps on doing that until the inside and outside pressures have equalized. And that's why you end up with the zero there on the graph during inhalation. All right, so that's steps 1 and 2 done. Next, we have expiration. And again, over here, your diaphragm is going to relax. So it's going to go from that flattened shape back to the dome shape, and your thoracic space will decrease or shrink, and your interpulmonary pressure will rise because there's less volume for the gas to occupy. It's going to be jostling and pushing other gas molecules next to it more frequently and intensely. So that's the change you see on the graph on the right as well. You can see the pressure rises during expiration above the atmospheric pressure. And again, we come back to zero, and that should make sense here again, because sure, our pressure will rise inside the chest cavity and in the lungs. But as a result of that, gas will want to leave and reach the outside with this lower pressure. So gas will start to exit and air will leave until the inside and outside pressures have equalized. So it's important to understand that the changes in pressure that happen during inspiration and expiration relative to the outside are transient or temporary, because what's happening is that gas is either going to move in or out to ensure that in the end, the pressures inside and outside are the same. All right, so that's intrapulmonary pressure, and it can get a bit confusing to understand how the pressure changes work. So I really recommend you have a look at these slides and see if you can just look at the graph on its own and logically step through why the graph has the shape that it has. But once you do that, we can move on to the next topic, which is describing the changes that happen within the pleural space. Now we're going to have a look at the intrapleural pressure, and that's the pressure within your pleura. So intrapleural within pleura. And that again refers to your pleural cavity or the pleural space. Anatomy-wise, that's the space that's enclosed between your visceral pleura surrounding the lung itself and stuck to that organ. And you can see that very, very briefly over there. And your parietal pleura is another layer that's stuck to the actual thoracic wall itself. So you can sort of think of it as being there. So parietal pleura stuck to the wall, visceral pleura stuck to the organ itself. And between the two layers is the pleural cavity or the pleural space. It doesn't contain anything inside it except for a bit of serous fluid to reduce friction between the two layers when your lungs are rubbing up against the wall. But there is no way for things to enter or exit the space. So it's a closed space and it behaves very differently to your pulmonary space. Again, your pulmonary space, if you remember, was able to exchange gas very clearly with the outside atmosphere. So air could enter your pulmonary space, your lung space, and leave your lung space as well through inhalation and exhalation. The same can't happen here. So let's have a look at how the pressure compares in your pleural cavity or your pleural space. So very importantly, your pleural pressure starts off as being negative, right? And then when you inspire or you breathe in, what happens is your lung expands. And as your lung expands, the space between the lung and the thoracic wall decreases. And in doing so, your pressure actually drops. So that's a bit different to our previous example. We saw in our previous example, when the lungs shrank or the thoracic space shrank, the pressure inside that container rose. But because the pleural space is a closed space, here what's happening is when your pleural space shrinks or becomes smaller, your pressure actually drops here instead of rising. So very important to keep in mind. And then during expiration, the opposite happens. During expiration, your lungs are going to shrink. And so the space between your thoracic wall and the lung, the pleural space, is going to increase. And again, over here, the opposite happens where when the pleural space expands, instead of the pressure actually dropping, it's actually going to rise. So just good to keep in mind that the pressure changes that occur within the pleural space are sort of different to the ones that occur in the pulmonary space. And again, you might wonder, why doesn't it become zero the same way that the inspiration and expiration cycles do in the intrapulmonary pressure? Well, if you remember, the reason that we actually reached zero at all in this graph was that the pulmonary space was able to exchange gas with the outside environment to equalize. So when during inspiration, the pressure became lower, what was able to happen was it was able to let air in so that it could reach the same pressure as the outside. During expiration, when the pressure rose, it was able to let air out so that it could, again, become equal to the outside. But this is an enclosed space. Things like that can't happen here. So it will just go down during inspiration and then come back up during expiration. And again, I invite you to pause at this point, look at the graph and see if you can work your way through that on your own. Here's a little animation on the left here, which hopefully provides a bit more of a visual way of understanding this. And again, if you want an analogy for understanding how pleural pressure works or intrapleural pressure works, think of the same syringe example, but instead think of the tip as being sealed or closed off. And so you can see here, when we try to pull back the syringe and actually increase the space inside the syringe, it actually makes the pressure rise and it'll resist you pulling the syringe. You can actually feel it if you try it with a syringe, and it'll want to return back to its original position. And so that's sort of what's happening here as well. And it points out an important role that the pleura plays in making sure that the lungs return to their original expanded state following the end of inspiration, following the end of expiration. To the topic of factors that actually influence ventilation. So how effectively we can breathe in or out. There are two main factors, lung compliance and airway radius. We're going to have a look at lung compliance first. So lung compliance refers to how easily the lungs can stretch, and that has a subcategory, which is elasticity, and that makes up 1/3 of lung compliance roughly. So elasticity depends on the lung tissue itself and its consistency. So lung tissue that has more connective tissue in it, so a thicker layer of that, has more elastin and more collagen, and it's going to be less compliant. It's going to want to stretch less. And so you can think of it as being more rigid. So the less compliant something is, the more rigid it is. And that means it's going to be more elastic recoil. So what that means is that even though being thicker and rigid makes it harder for the lungs to expand, it gives it the bonus or the added benefit of being able to recoil back more because it's more sort of elastic. So this comes into play in a clinical context in pulmonary fibrosis, where there's a lot more fibrous tissue. So your lungs won't be able to expand as much, but they can for sure recoil much more strongly. And we'll look at the implications of that for spirometry during a later video. Next up, we have surface tension, which accounts for much more lung compliance than elasticity does, about double it. And surface tension is a force that resists expansion, right? So surface tension within the alveoli is going to resist the alveoli trying to expand. And so it'll resist air coming in and trying to push the lungs open. But there is another factor, which is called surfactant. Surfactant is a chemical produced by type 2 alveolar cells within the lungs, and it's usually produced by them during gestation, right? And what this molecule surfactant does, or molecules do, is they reduce the surface tension by reducing the hydrogen bonding between water molecules. And therefore, if you reduce that surface tension, there's going to be less resistance to expansion, and your lungs are going to be able to be stretched more easily, and therefore you can describe them as more compliant in this case. And so it's really important that you have that surfactant, otherwise your lungs are going to be really hard to open up. And clinically, this comes into play during infant respiratory distress syndrome, where if your alveolar cells don't produce that surfactant during gestation, it's going to be very difficult for a newborn to be able to breathe, and that can be very difficult. Next, we come to the topic of airway radius. So this one is a bit easier to understand, but we'll talk about the bronchial tree first. So as you know, your trachea divides into bronchi, which divides into bronchioles, and which become terminal bronchioles, respiratory bronchioles, and along that pathway it keeps bifurcating. And in doing so, it creates more branches, but those branches are also smaller than the original branch that came off of. And the important idea here, again, is that as the radius of the pipe that air is going through becomes smaller, it becomes harder for the air to go through it, right? So the actual relationship that exists is that the flow, or how easily air can pass through a pipe, is related to, inversely proportional to the radius of that pipe. And another mathematical thing to keep in mind is that the resistance to flow is related to, or proportional to, the length of that pipe over the radius of that pipe to the power of 4. And again, just a couple of things to keep in mind. These mathematical relationships can pop up a little bit during exams, but just keep those two relationships in mind. Another small fact is that the resistance of your bronchioles is greatest in the medium-sized ones, which I think you can see right about there. Yeah. All right, the next topic is autonomic control. So as you know, your respiratory system, specifically the airways, have muscle surrounding them, smooth muscle, and that smooth muscle is under the control of your parasympathetic and your sympathetic system. So your parasympathetic system, when it's activated, that's your rest and digest mode, right? You don't really need your airways to be as open because you're resting and digesting. You can sort of relax a bit more. And so you can think of that as being the reason why you have bronchoconstriction happening and your airways become narrower as the muscle, smooth muscle around it contracts. And the key chemicals to keep in mind here are acetylcholine from your parasympathetic nerves affecting muscarinic receptors on that smooth muscle cell. And with the sympathetic nervous system, what's happening here is the opposite because it's your flight or fight response. And during this one, you're going to have bronchodilation occurring to get more air into your lungs. And the key chemicals to keep in mind here is adrenaline acting on beta adrenoceptors. So the last thing to keep in mind there is reflex bronchoconstriction, which is a sort of a smaller side note. And the idea is that inhaled stimuli like cigarette particles, dust, cold air can actually cause your bronchioles and your airways to reflexively constrict to almost protect itself from that harm. And finally, we come to investigations, which is spirometry. And this is a way we can assess lung function, specifically ventilation. And the way it works is you put a clip on someone's nose so that they're not breathing through their nose and only breathing through their mouth. And then you ask them to initially just breathe normally, so you get their tidal volume and tidal breathing. And then you ask them to take a deep breath in and then breathe out as hard and as fast as they can. And that also allows you to assess a number of other parts of lung function. Again, we'll be going over that in a dedicated video about lung function tests later on. So I hope you found that useful. And again, if you have any questions, feedback, or concerns, let us know in the comments, message any one of us, or reach out to us in any way that you can, and we'll try to get back to you as soon as possible. And we'll see you in the next one.